Okay, so McLaurin, first of all, has an I here, not an E, so I think I typed it wrong on your paper there. You can fix that. Does anyone need this handout? Everyone has this handout from yesterday? I have extras, so. Okay, let me see if I can find my extra here. Okay, so the first thing it says to do on this worksheet is to find the derivatives of all orders. All orders. So that just means since this has 6 powers of x, you're going to find the derivative 6 times. Okay? So let's see what happens. If I take f prime of x, that gives me, now remember a, b, c, d, e, f, g, and h are all constants. And also, do you guys have a, b, c, d, f, g, h, or do you have a, b, c, d, e, f, g?
F.
Okay, I think there's a typo there, and there. So you guys need to fix these to E, F, G. It should not be F, G, H. So if you guys could fix that before we start, that would help. Okay, so what is the derivative, the first derivative? Well, this first term would just vanish. So it would just be b plus 2cx plus 3dx squared plus 4ex cubed plus 5x to the fourth, 5fx to the fourth, plus 6gx to the fifth. Right? Okay, now go ahead and find the second derivative, and the third derivative, and the fourth derivative, and so on. Until you reach 0. It might not be fun, but it is pretty interesting what comes out of it. And it's fun.
It might not be.
Your second derivative should just be 2c plus 6dx plus 12ex squared plus 20fx to the third. And then we have 30gx to the fourth. For third derivative, we use triple prime. Does anyone know what we use for the fourth derivative?
d4x over dy is 4.
You can write d to the fourth f over dx to the fourth. You can write that, or you can just write a little 4 in parentheses here. The parentheses means it's not a power, it's a derivative. So this means the fourth derivative. Or you can use the Roman numeral IV, lowercase. So IV. But that's kind of awkward when you reach like 19, you know, when you're writing XIX or whatever. So let's just, why don't we use the parentheses notation for fourth derivative. Okay, I'm filling it out up here too in case you get stuck or you want to check your answers.
Wait, don't you need to get this? You need to do it to 0, right?
Yeah, we're going to go all the way.
Seventh derivative?
There's technically 6 derivatives altogether. The 7th one is 0, so we won't even really use that one.
Okay.
Yeah,
So
we
we
won't
don't
really use
have
that
to
one.
do.
You don't really have to do the 7th derivative. And I need room for one more derivative in here. You don't like this? I thought you would like this. Oh well.
It's nice because I actually know how to do something still. Rather than looking
Yeah,
at
this is not a new concept, right? We're just doing something more than we normally would. You could be grateful it was a polynomial and not some other function. Although you might have wished it was e to the x. In which case it would have just been e to the x, e to the x, e to the x, e to the x, all the way down.
Yeah, but you would never get to 0, isn't that kind of the point?
Yes, you're right. Okay, well, if you look at page 3 of my notes, we are going to do e to the x. Okay, so what just happened? We just basically did the derivative multiple times. Now what we're supposed to do, it says, is evaluate the function and all the derivatives at x equals 0. So before you freak out, we're plugging in 0, right? So
So it's just
f
the
of
first one.
0 is literally just a, right? So f of 0 is a. F prime of 0 is what? Notice you're plugging in
B.
0. So this is just b. What's f double prime of 0?
C.
2c,
Oh.
right? Look at your derivatives there. What's f triple prime at 0? 6d. The fourth derivative at 0 is 24e. The fifth derivative at 0 is 120f. And the last one, the sixth derivative at 0, is 720g. I ran out of room. Wouldn't you believe it? The sixth derivative at 0 is 720g.
It's almost a full kilogram.
Okay, so I got the joke. 720 grams. So you're going to be now reconstructing. You're going to reconstruct F, but this time without any A's, B's, C's, D's. Okay, so now we're going to isolate A, B, C, D, E, F, and G in these expressions we just wrote. Okay? So let me scroll down here. So it says solve for A, B, C, D, E, F, and G. There's no H. In the resulting equations. All right, let me give myself a little space here. So A is f of 0. A is f of 0. B is f prime of 0. C is 1/2 f double prime of 0. D is 1/6 f triple prime of 0. E is 1/24 times the fourth derivative at 0. F is 1/120 times the fifth derivative at 0. G is 1/720 times the sixth derivative at 0. Does anybody see a pattern? Anyone see a pattern? Do you guys know these numbers? 1, 2, 6, 24, 120, 720. Let me ask you a question. Where did this 720 come from?
2 times 360.
It was from 2 times 360. Actually, wasn't it 6 times 120? Look back at your work, right? When we did the multiple derivatives, right, back a few steps. Let's all stare at that 720 for a minute. Where'd that thing come from? I kind of scribble all over it now. Hugh found the pattern. Don't say it again because someone else might get it without thinking. And that's not good. This 720, listen, this 720 came when we took the derivative of 360g x squared. Remember that? We multiplied, yeah, 2 times 360, you're right. It was 2 times 360. And that 360 came from when we multiplied the 3 times 120. See? And this 120 came when we did 4 times 30 earlier. And the 30 came from doing 6 times 5 earlier. Right? So one way to think of this is you could come back down here now and look at these. You could think of this as G is really 6 times 5 times 4 times 3 times 2 times 1 times the sixth derivative. I mean, 720 is literally 6 times 5 times 4 times 3 times 2 times 1. Also known as what?
6 factorial.
Yes. So it seems like there's some kind of a weird connection between the coefficient g, the 6th factorial, and the 6th derivative. So I'll say that again. The 6th coefficient is 1 over 6 factorial times the 6th derivative. Very interesting connection. So I'll abbreviate what I just wrote. You know I can use the factorial symbol, right? So let me do that. It is no coincidence that this is 1 over 6 factorial times the 6th derivative at 0. In fact, we can actually rewrite the whole polynomial like this. Watch. Here's the original polynomial f in all of its original glory. But it looks a little new now. Instead of a, I'm going to write f of 0 over 0 factorial.
Wait, you can't
Then
do
I'm
that.
going to write the bx as f prime of 0 over 1 factorial x to the first. That's bx. Then I'm going to write f double prime 0 over 2 factorial x squared. That's cx squared, you see. Then f triple prime at 0 over 3 factorial x cubed. That's dx cubed. I'm just substituting, for d, I'm substituting in the 1 over 6. F triple prime, and yes, you can have 0 factorial to 1.
Okay.
Just defined as 1. Next is 1 over 4 factorial times f quadruple prime. So basically, the fourth derivative at 0 over 4 factorial times x to the fourth. When you write it like this, the pattern is obvious. And profound. It is very interesting. If you had basically a degree n polynomial, if the degree of the polynomial was not 6, but n, the nth coefficient would be the nth derivative at 0 divided by n factorial x, and it would be in front of an x to the n, of course. That's an n factorial. So if the degree were n, a random coefficient deep down in the polynomial would be the nth derivative at 0 divided by n factorial. So if, let's say you had a 1,000 term long polynomial, the 997th term would be 1 over 997 factorial times f, the 997th derivative evaluated at 0. Okay, question or comment? Okay, cool. That's even better. Okay, so this was an idea that was stumbled upon by, well, the two guys that got credit for it were Maclaurin and Taylor. Those are their last names. Okay, they're both British mathematicians, English mathematicians, and they both kind of contributed to these ideas, rewriting a polynomial in terms of its own derivatives. Very clever. Now let's go on to this next problem. We're going to see something interesting happen when we try this with sine. Okay? First of all, sine is a little different, isn't it?
Yep.
What makes sine different?
It repeats.
We can take the derivative many times, but we'll never get to 0. Right? So we're going to steal the same concept from the previous problem. We're going to assume that this can be written as sigma n equals 0 to infinity something. We're going to assume it can be written as an ax. We're assuming that it can be written like a plus bx plus cx squared plus dx cubed plus something. Okay, we're going to assume that a, b, and c, and so forth exist, first of all. That's an assumption. But we're going to steal the idea from the previous problem and use that to create a, b, c, d, etc. Okay? All right. So we're going to find the coefficients of a sine wave polynomial version, basically. Okay, so to do this, to get a, basically, we're going to need, to get a, b, c, d, etc., we're going to need the derivatives. So let's see, the first derivative, what's f prime? The ratio not working too well. Let's check. F prime of x is what? Cosine x, right? Okay. F double prime at x is what? Negative sine x. F triple prime at x is? Negative cos x. And the fourth derivative is? Back to sine x. And this kind of repeats itself, doesn't it? The fifth derivative is back to cos x. Evaluating at 0, f of 0 is sine 0, which is 0. F prime at 0 is cos 0, which is 1. F double prime at 0 is negative sine 0, which is 0. F triple prime at 0 is negative cosine of 0, which is negative 1. The fourth derivative evaluated at 0 is sine 0, which is back to 0. And the fifth derivative at 0 looks like f negative 5. Pen's not working too well here, guys. Give me a second. There we go. Is back to cosine 0, which is 1. In other words, it looks like the coefficients which are related to the derivatives are going to be things like zeros and ones and negative ones. Okay, so I'm going to do my best to create sine using the same idea I had on the previous page. On the previous page, I said that f of x could be expanded as a plus bx plus cx squared plus dx cubed, etc. Right? Here I'm saying that sine x can be a, which is 0, I guess, plus bx. B would be the first derivative over 1 factorial. Next would be cx squared, which is going to be the second derivative over 2 factorial, x squared. The third term would be the third derivative over 3 factorial, x cubed, and so on. So let's fill in a few more terms. The next one's going to be 0 over 4 factorial times x to the fourth, followed by 1 over 5 factorial x to the fifth, followed by, you guessed it, 0 x to the sixth over 6 factorial, then I'll switch back to negative 1 over 7 factorial over x times x to the seventh. And this pattern probably goes on forever because we don't know when to stop.
So that's why it goes plus minus, 0 instead of plus plus, but both of them are positive.
Yeah, so it turns out that all the even terms do vanish. They all happen to have the derivative being 0. And that's because all the even derivatives of, actually I should say, yeah, all the even derivatives of sine vanish when you plug in 0. Okay? So now I'd like to sort of put all this together and see the pattern more clearly. So the pattern is actually not very hard to see at all. It's definitely odd everything, right? So you could say, you really could, that sine x is the same as just x minus 1/3 x cubed plus 1/5 x to the fifth. Sorry, these are 3 factorial and 5 factorial. Excuse me. And then minus 1/7 factorial x factorial. What am I doing? I'm writing this incorrectly. This should be an x to the fifth and an x to the seventh. This is what happens when you don't have water in your system. Drink water. There we go. And this pattern just goes on forever. It would be even more helpful if we could put it into a sigma notation. So we can express all of it at one time. So let's put this into one big wambooey. If we start at 0, this goes on forever. The denominators include 1, 3, 5, 7, and they're all factorialized. So we could just call those guys 2n plus 1 factorials. The top, it's really just an x, but the power is the same as the factorial on the bottom. And this is the power series representation of sine x. Okay, very cool. This is sine x.
So this isn't, instead of using like the other one where you can derive both of them and then.
What do you mean?
A different way to find it.
What do you mean?
Because the other time we found sine x and stuff like that. Oh no, we proved the reverse. Never mind.
Yes,
That was
in the
sine
warm-up
x.
a few days ago, I gave you this formula, and I said, can you show that it converges for all x? Actually, I said, can you tell me which x's make this series convergent? And what you guys did was you set up a ratio test, and you showed that it didn't matter what x was. This statement, this series is always convergent. So that's actually what I was going to do now. I was going to repeat that warm-up exercise. Okay? All right, so here it goes. First, we set up a ratio test. Nth term is on the bottom. Oh, I forgot the alternator. For the alternator, guys, do you think we should use... Which one do you think we should use?
-1 to the n.
-1 to the n?
Because, well, I mean, if you're proving it's sine or...
It's got to alternate.
Shouldn't it?
Is it -1 to the n, or is it -1 to the n plus 1? That's important. We got to decide. If you plug in 0, it's going to give you positive. Does that match up well with our series? Is our first term, the 0th term, positive? Seems it is. Okay, so this is a good alternator to use for that. So anyway, there's a -1 to the n right here. The n plus first term has a -1 to the n plus 1. Then it's x to the 2 times n plus 1 plus 1 all over 2 times n plus 1 plus 1 factorial. So we're doing a ratio test. The absolute value, you know, kind of ruins the need even for these -1 to the n's and stuff. You don't need any of that because of absolute value. And you basically have x to the 2n plus 3. This is a 2n plus 3 factorial. On the bottom you have an x to the 2n plus 1 and a 2n plus 1 factorial. If the outer is the numerator and the inner is the denominator, we can write this again. I think my computer finally said I'm done for the day.
It's too hot outside.
Maybe it's too hot outside.
It's too hot.
Pen? Can I still use the pen? Thank you. Okay. If you do inner denominator, outer numerator, you end up with x squared here, and you end up with basically a 2n plus 3 and a 2n plus 2. Everything else cancels out in this problem. Now we're going to force convergence, because we want to study the x's that make it converge. So we could pull out this absolute value x squared and then perform the limit on just the n garbage.
It just goes to 0, right?
Yeah, and since this part vanishes anyway, or this goes to 0, we're kind of pigeonholed into believing that x could be anything, because 0 is always less than 1, no matter what x is, for all x. So this is true for all x. So what is our takeaway on this problem? We're saying that sine x can be written like this, and this formula is good always. This is important, because our granddaddy macho was only good for -1 to 1, but this formula is good everywhere. So now I'll just show you real quick with the computer how we can kind of demonstrate that. You can also do this on your graphing calculator. Okay, let me delete some old garbage here. All right, so you guys know sine x looks like this. Yeah, the bell seems tired too. It's been a long week. I'm going to just type in the first 5 terms, you'll see.
On Monday, y'all. Get hyped.
So I'm just putting in the first several terms here, but even with just a few terms, you can see this is going up to x to the 7. Look at that tight fit. That brown thing fits the black perfectly. And if we keep going, it will fit the whole curve, not just -1 to 1, you know. Okay, so that's a pretty cool takeaway. Memorize that guy. He's called the Maclaurin series for sine. Have a great weekend.
So McLaurin
Finish your
and
worksheet.
Taylor found it, but Taylor got screwed.
Well, actually, Taylor found how to do this not just at 0, but at any point. And Maclaurin did it at 0, but technically, the Maclaurin series is a Taylor series just at 0. And then Taylor series are more versatile. You can do them anywhere. So,
See you guys show. Have a good weekend.
okay, see you later. Okay, let's go back to the drawing board, and now let's look at e to the x. I'll let you try cosine later, okay? All right, so e to the x is a fun one, because we know that f of x is e to the x, and we know that f prime of x is e to the x, and f double prime is e to the x, and this never changes, right? This just goes on forever. So what this means for us is we plug in 0 for every one of these. F of 0 is 1, f prime at 0 is 1, f double prime at 0 is 1, f triple prime at 0 is 1, and this goes on forever. So when we try to apply our logic from the previous 2 problems, we assume that all the coefficients are 1. So e to the x would be f of 0 over 0 factorial plus f prime at 0 over 1 factorial x to the first plus f double prime at 0 over 2 factorial x squared plus f triple prime at 0 over 3 factorial x cubed, and this goes on forever. Evidently the derivatives never stop, the coefficients never stop. So we have e to the x equals 1 plus 1 over 1 x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the 4th, etc. In other words, it doesn't even alternate, but it basically goes x to the ends on top, in factorials on the bottom. To show that this converges for all x's, we can just basically do a ratio test. N plus first term over nth term. Which gives us, this should be n goes to infinity, guys. Sorry, I put x goes to infinity for my limit. numerator, you basically get x to the n plus 1 here, and x to the n here. You have a n factorial here, and n plus 1 factorial here. See? So all of this simplifies down to simply x, and then we have the n factorial cancel out, and n factorial canceling out. I wrote that wrong on the bottom. That should be n plus 1 factorial times, I'm sorry, n plus 1 times n factorial. Same thing as n plus 1 factorial. Okay? So like that. And then this cancels out. And we're going to force convergence. We're going to make this less than 1. Make this less than 1. You can actually pull out the absolute value x if you like. But this is 1 over n plus 1 left inside. And the reason this is always going to be true no matter what x is because this limit is 0. So we're forced to believe that this is true for all x. Okay, again, I think we should go to the grapher and see this happen. Okay? So to the graphing utility. This time we're taking out sine x. We're replacing it with e to the x. We're replacing this with a simpler pattern actually. It's 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial. So that's just 6. Plus x to the 4th over 4 factorial, that's 24. Plus x to the 5th over 5 factorial, that's 120. And let me zoom out a little so you can see better. And let me change the colors because brown on black is hard to see. Let's do a bright pink. And I zoomed out a little too far. Okay, so the e to the x curve is right over here. Okay, there's your e to the x curve. And here's the polynomial. Look at that tight fit. Wow. E to the x fits right in here like this. Where does it start to diverge apart? Well, let's zoom out a little so we can see that again. Now that you can see both curves. Zoom out. Or actually I could just scroll up. It is separating a little bit. So I'm out here at x equals 3. You can see them starting to spread apart a little bit. There they go, see them? This is just because I only did the first 5 terms. I only went up to x to the 5th. So if I had gone any higher, I probably would have gotten more accuracy and a tighter fit still. And the theory on this is, since we proved this is true for all x, it converges for all x. Maybe we should have written converges for all x. It's a little more meaningful. What it means for us is that if you keep adding terms, you will actually be able to model the entire e to the x curve, the whole thing. So the infinite series is exactly the whole curve, not part of the curve. Okay? So our takeaways for this lesson are, put down the takeaways so we can have everything in one place. You're kind of out of space, but let me go ahead and add a page here to my document. Clean up this mess. In a second. Okay, so the takeaways for us could be that we saw sine x can now be written as n equals 0 to infinity with an alternator and an x to the 2n plus 1 power and 2n plus 1 factorial. E to the x can be written in the same format. This time it's a little simpler. It's just x to the n and it's n factorial. Both of these converge for all x's, so the interval of convergence is all real numbers. But let's write negative infinity to infinity, because we usually write our intervals of convergence as inequalities like this. And we would also say the radius of convergence is infinite. I'll let you do cosine on your own time, or maybe as part of a worksheet. Hope you have a nice weekend, and don't forget to finish up your worksheet 6. And also, for the 2014 students, you guys are still working on worksheet 6. And make sure your notes are in order and you're constantly reviewing them.